welcome to day 17 of calculus. Today we're going to talk about shortcuts for finding derivatives of polynomials. But before we get to that, we're going to practice graphing derivatives first. So given f of x in each of the graphs below, so this is f of x. This function right here is f of x. You can assume it continues on. Graph the derivative. So we don't have a function, we don't have the actual equation for the function, we have just the graph. So if we have just the graph, we're going to make an estimate for what we think the derivative looks like, and there's some important things to start with. Start with places where the derivative is 0, and that's where the tangent line will be horizontal. And that looks like it's going to occur right about here at the top. Tangent line is horizontal here, and tangent line is horizontal there. So that's where the derivative is 0. At those points. So I'll leave those red points in there. So the derivative looks like it's 0 here and here. So that means that the derivative function will be 0 there and 0 right there in those two places, because the tangent line has a slope of 0 at each point. So what about the rest? Well, from here to here, the function is increasing. So that means that from there to there, we know that the derivative is positive. It stays positive, and then it gets less and less positive as it gets to here because it's 0 right at that point, and I'll keep it red right there. Where else is the derivative positive? The derivative is positive here. The derivative is positive right there. So where it's yellow, the derivative is greater than 0. The function is increasing. Where is it decreasing? Well, it's decreasing from here to there. It's going down. It's going down. So from there to there in the blue, the derivative is less than 0. The key thing to realize is as you travel along, it's really steep, it's less steep, it's less steep. It's still positive, it's less steep, and then it's 0. So what's going on is that it's going from really big positive all the way down to 0. But then with the blue, it's going to start out a little negative, then more negative, then less negative, then back to 0. So what's going to happen is it's going to be negative, and then it's going to come back up. But then what happens here? Well, it's going to get a little bit positive, then really, really positive. It's going to go back up. So you end up with a graph that looks like that. Looks kind of like a parabola. So again, the yellow is where the function is increasing, the blue is where it's decreasing, and the big red dots are where the derivative is 0. So again, you can't really be perfect because you don't know what the actual function is, but in general, this S-shaped function ends up looking like a U shape when you take the derivative. So let's do another one. What about here? Let's do the same process. Where does it look like the tangent lines are 0? Well, there, at the top there, and at the top there. So we know that the derivative is going to be 0 here, here, and there, because we go straight to there, we go straight down to there, we go straight up to there. Where is the function increasing? It's increasing from here to here, and it's increasing here. So wherever it's yellow, it means the derivative has to be greater than 0. And then where is it going to be negative? Well, it's negative everywhere else. It's decreasing, and it's decreasing. So it's positive where it's yellow, so it's going to look like this here. And where is it also going to be yellow? Where is it positive? It's positive right here. It's going up. And then in between, wherever it's blue, it's going to be negative, so it's going to keep going down. And then here, it's going to go down and then up. So look what happened here. Wherever it's blue, the derivative has to be below the x-axis, and look, it is. Wherever it's blue, this is below the x-axis, and wherever it's yellow, that's where the function is increasing, so it has to be above. You can also kind of look at where it's steepest. Where does it look like it's steepest? Well, it looks like it's steepest right about here, so that should correlate to the highest point there. Looks like it's steepest right about here, so that should correlate to the lowest point there because it's negative. So do the zeros first, identify where the function is going to be increasing, in this case where it's yellow, and where the function is decreasing, where it's going to be blue, and then you connect it with a smooth curve. So again, what did we notice? We noticed that a function that looked like this, which is a cubic, the derivative turned into a quadratic, and then on here we noticed that a function that would be a 4th degree polynomial turned into a cubic. So we went from cubic to quadratic, and we went from quartic, 4th degree, to cubic. What this actually tells us is that if f of x is equal to a n to the x, I'll write this big, f of x is equal to a constant times x to the n, the derivative is actually equal to a times n times x to the n minus 1. What that means is, for example, if f of x was equal to x cubed, what you do is you bring the 3 to the front and subtract 1, and then you have the derivative. The derivative would be 3x squared. Let's say g of x was 2x to the 9th. The derivative would be 2 times 9 times x to the 8th, or 18x to the 8th. This only works for things of this form right here, ax to the n, where a and n are both constants, This is the awesome shortcut. So what about linear functions like this? Well, what's the power? Is this of the form ax to the n right here? It certainly is, because there's a power of 1 right there, a power of 1. So f prime on this one, you drop the 1 to the front, it's 1 times 2 because it's already there. X, well, what's 1 less than 1? Well, it's going to be 0. X to the 0, remember, is equal to 1, so this is just going to be 2. Which kind of makes sense, because if you have the line 2x, what's the rate of change of at every single point? 2. What about here? Well, that still works. We know that the derivative of that is going to be 2. But what's here? There's actually an x to the 0 right there. Is there an x to the 0 right there? Well, x to the 0 is just 1. So in this case, what is the slope of a horizontal line? That's the thing you can think about. If this was just a horizontal line, y equals 4, what's the slope? The slope is always, what's the rate of change? 0. So in this case, f prime of x is equal to 0. So let's go over here. Well, the derivative here, as we've seen, when it's just a line, the rate of change is the coefficient, so it's going to be -3. And this is just a constant right there. This one is just a constant. The definition of constant means unchanging. So what's the rate of change of a constant? Well, it's 0. So the derivative here is just -3. The moral of the story here is that the rate of change, the derivative of a line, is always just going to be the leading coefficient, regardless of the constant. What about here? Remember, you drop the power to the front, keep the coefficient, and then drop the power by 1. So it's x to the 2 minus 1, so that's going to be 12x to the first, or just 12x. What about here? Well, that's going to be f prime of x. Do the same thing, 2 times 6 times x, 2 minus 1 is 1. The derivative of a constant is 0, so this is just plus 0, so 12x. And what about here? F prime of x is equal to 3, drop the 3 to the front, the 4 stays, x to the 3 minus 1. It's going to be 12x squared. So you'll notice that some of these will come out to be the same, some of them different. Different functions can have the same derivative. It's pretty cool. So before, filling in a table like this would be pretty hard, because we'd have to use the limit definition, which I know you just love, f of a plus h minus f of a over h. And you will still have to use that for things that aren't polynomials, because this rule only works for polynomials. But now we have a quick way of finding f prime. So if we do that for this function right here, f prime of x, the derivative will be, drop 3 to the front, multiply it times -4, and reduce the power by 1, so you get -12x squared, plus 3 times 2 is 6, so plus 6x, because it's x to the first, minus 2, and then the derivative of 1 is just a constant. So now all you need to do is plug these numbers into the function and into the derivative. So now it's just a matter of plugging the numbers into the two functions, and you can complete the table. This rule allows you to find the derivative really quickly. Let's go back to our favorite tangent lines. So if you have this function g of x, if you want to find the equation of the line tangent to the function at x equals 1, again, we need two things, the point and the slope. And in general, the easier one is the point. So for that, we know that its x is 1, but we need the y value. So we do f of 1, so that's going to be -4 times 1 cubed plus 2 times 1 squared plus 5 times 1 minus 4. So you end up with -4 plus 2 plus 5 minus 4. So that's going to be -8 plus 7, which is -1. So we know the point is 1, -1. So we can fill that in 1, comma, -1. What about the slope? Well, before we had to use the difference quotient, but now we can just find the derivative. If we do the derivative, it's going to be g prime of x will be, you drop the power to the front, so it's -12x squared. This goes to the front, reduces by 1, so it's going to be 4x plus 5. Again, derivative of a constant is 0. So now all you need to do is g of 1. What is the rate of change at the x value we're at? We're at 1 right here. So g of 1, g prime, excuse me, g prime of 1 will be negative 12 times 1 squared plus 4 times 1 plus 5, which is negative 12 plus 9, which is negative 3. So we just found out that the slope is indeed negative 3. Now we know the point slope is y minus y1 is equal to m times x minus x1. We end up with a function y minus negative 1 equals negative 3 times x minus 1. Clean it up just a little bit and you end up with y plus 1 is equal to negative 3 times x minus 1. So the key new thing is this process was the same, but we didn't need to use the difference quotient. We could just use our new shortcut to find the derivative, and then it tells us really nicely what the rate of change is, the slope, and it allows us to write the equation of the line. But nothing really changed. We still needed a point and a slope. The key thing to realize here is that this new shortcut, where g of x is equal to ax to the n, lets you have g prime of x is n times a times x to the n minus 1, only works for power functions,